Okay, let me start from PDF page. I go by PDF page 22 and this one. 2.2 Kronecker delta and permutation symbols. Let me check this YouTube. I don't know if this is working. I think it's working. PDF page 22. Okay, it's working. I think it's working. It's okay. Okay, so Kronecker delta and permutation symbols. These two notations are extremely useful in connection with Cartesian coordinates. The Kronecker delta is defined as delta ij equal 1 if I equals j, 0 if I not equals j. This definition assumes that I and j are explicit integers such as I equal 1, j equals 3, and it does not imply delta ii equal 1. Elements. I think you already know about this one. Delta ii actually means delta 1 1 plus delta 2 2 plus delta 3 3. So this means 3. Anyway, elements of Kronecker delta corresponds to the elements of the identity matrix I delta ij I1 0 0 0 1 0 0 0 1, which with this delta ii equals j, delta ij delta jk is delta ik. Why is this so? So let me try this. Delta ij delta jk equal like this. Delta I1 delta 1k plus delta I2 delta ik another 2k. So this is like 2k plus delta I3 delta 3k. Yeah. So we have to have a condition. So this you have to have condition. If I equal 1, then this is so if I equal 1, this is 1. So we have delta ik 1k here. Okay, I can say ik. If I equal 2, so this is 0, I equal 2, this is 1. So we have delta ik. Here I equal 2. If I equal 3, this is 0, this is 1. So I equal 3, this is delta ik. So anyway, we see this everything is delta ik. So this okay. Delta ij a jk I think same logic takes place here. So then we have this. Delta ij, ajk is delta jk. Delta ik. I'm sorry. Delta ik. So the permutation symbol or alternator is defined as epsilon ijk is 1 if ijk are even permutation of 1, 2, 3. This even permutation is like 1, 2, 3, 1, 2, 3. So you can do anything like 1, 2, 3, 2, 3, 2, 3, 1, 3, 1, 2. These are this even permutation. If ijk are odd permutation of 1, 2, 3, so odd permutation means, for example, you have 1, 3, 2, 3, 2, 1, 2, 1, 3. Yeah, these are 1, minus 1. Then otherwise 0. From the preceding definition we have, let's see, epsilon ijk, epsilon, I don't know. Oh, okay. Here it's E. I'm sorry, this is E. But in many cases we use epsilon. We use epsilon, not E. In here like epsilon ijk. I think this is more common, epsilon ijk. This is more common symbol for this purpose. From the preceding definition we have so I call this epsilon instead of E. Epsilon ijk, epsilon jki, epsilon kij equal minus ikj minus jik minus kji. Yeah. Epsilon ijj or jij or jji equals 0. Explicitly we have epsilon 1, 2, 3 equal 2, 1, 2, 3, 1, 3, 1, 2 equals 0. Epsilon 2, 1, 3 equal epsilon 3, 2, 1 equal epsilon 1, 3, 2 equal minus 1. Figure 2.1 shows the order of the indices for even and odd permutations. Figure 2.1 even and odd permutation of the integer 1, 2, and 3. So this is even. This is even and this is odd. Using the permutation symbol, we may express the determinant of a 3 by 3 matrix A as determinant A is, see, I think everybody knows this. So if you have determinant, we just do this way. And if you have 2 entry here, this way, and you have 2, 3, this one, this one. Yeah? This one is this. Let me use color. This one is this. Okay? 1, 2, 2, 3. Oh, Yeah. So it's okay. So then this second one, let me use green. This one is this green. Yeah. So then we have let me use this one. So this one. That's this. Then we go opposite diagonal. Yes, so let me use orange. This one is this. Let me see. The better one is 1 3 2 2 3 1. So I use this one. This one. Then maybe purple. Let me delete this. Purple 1 1 2 3 3 2. This one. This and this one. This. And that's this. Then the last one is this pink. This one. So in one diagonal or how do you call this? Naname. I can use Japanese. Naname. Naname is this, This is naname. This or this is naname. So I don't know how to say this in English. Naname. Diagonal. Slanting. Okay, diagonal. I thought a diagonal is more like if you have square, I thought diagonal is this diagonal. But naname this is also naname in Japanese. These are all naname. I don't know in English diagonal. Diagonal also means this. I thought the diagonal in English is just this or this. But anyway, so all diagonal product. So one way diagonal product in one way has the sign plus. Diagonal product in the other way has a sign minus. So that's how to calculate determinant for 3 by 3 matrix. So then if you see, okay, let me delete this. delete this, and you see I 1 2 3 1 2 3 1 2 3. So here everything 1 2 3 1 2 3 1 2 3, right? So then ijk, the other one here, let's see the other one. The other one is 1 2 3 2 3 1 3 1 2. Yeah? So if this ijk is a permutation of 1 2 3, even permutation of 1 2 3, you have sign plus, and here is ijk, odd permutation of 1 2 3, 2 1 3 3 2 1. These are odd permutation of 1 2 3. In that case, you have a sign of minus 1. Yeah. So then summation go like this. You have II. So you can in this way you have, I don't know how do you say, you have 1 2 3 A1 A1 1 A1 2 A1 3. I think you can do this way. Here you can consider this one E1JK A11 A2J A3K plus E2JK A, this is I, 2I A, I'm sorry, I'm wrong. You can do 2I, I'm sorry, JK 1 I, this is I here is 1, I here is 1 1, right? Now we are considering a summation over I. So this is 1 2 A 2J A 3K, correct? So then plus E 3 JK A 1 3 A 2J A 3K, correct? So then we can also expand this first term now you can expand in terms of j, and you obtain something like this. E11k A11 plus A21 plus, not plus, this is a multiply, then A3k plus epsilon 1 to k A11 A22 A3k plus E13k A11 A23 A3k, something like this. Yeah, you can expand this way, and you can further expand this one. Further expand. I don't know why I expand. So I can write it here. This expansion. E111 A. I'm sorry. Here we can ignore this one. Yeah, this is because it's a II. Two indices are repeated here. 1, 1. So here two indices are repeated. So this whole thing is 0. Yeah, you can see 0. So then we expand actually the second one. This one. We expand this one. So let's see. Then we see 1, 2, 3, 1, 2, 1. So this is also 0. A11, A22, A31. This is 0 because you have 1, 1 repeated. So this is 0. The second term is this E1, 2, 2. Then this is also 0. A11, A22, A32. This is 0 because two indices, 2, 2 are repeated. Okay, so let me delete this. Oh, sorry. And finally, a non-zero term here is epsilon 1, 2, 3, right? Epsilon 1, 2, 3. Then this is A11, A22, A33. Then this epsilon 1, 2, 3 is 1. This is 1. Plus 1. What I say is plus 1. So in this way, we can expand. So a second term. This is, let me see, I can give you another color. This one. See? This one, from this one, you obtain plus epsilon 1, I'm sorry, this This has to be 1, 3, 2, A1, 1, A2, 3, A3, 2. Yeah, this is what we obtain. Then this epsilon 1, 3, 2 is minus 1. So what we can conclude here is from first one, from this first term, let me see, I can use red. This one, we have two terms. This term and this term. Then, from second term, we will have additional two terms. And then from the last term, we will have two terms again. So altogether, we have 6 terms. So this makes sense. This is 6 terms. Okay, let me delete. So there is another manipulation. IJK, IJ, J2, K3. This one you have to expand. See, this is the only way you can confirm. You can confirm this expression by expanding. Okay. To confirm this expression, you have to expand. Then you confirm this. This one you can also expand. And you can confirm this. Okay, the last one looks more complicated. I don't know how to prove this. So let me read the text. We can see the second and third expression as the first law expansion, as the law expansion and the first column expansion of the determinant, and last equation as the sum of all row expansion and all column expansion, which adds up to 6 divided by 6. I think see this one is more like you sum over I, sum over J, sum over K. Right? This is same. You sum over I. So this is more like it's two things. Yeah, the last one you sum over I, J, K, L, M, N. then you have to divide this by 6. I think you have to work out somehow. You have to work out. Please work out. Work out. Okay, so it should be okay. We can also express the determinant in terms of the cofactors of a matrix. For a 3 by 3 matrix, the cofactor of an element Aij is 2 by 2 determinant we obtain by eliminating ith row and jth column and multiplying it by -1 to the power I plus j. Let us denote this cofactor by Aij star. Then determinant A is Aij times cofactor of Ij star, no sum on I. Observing that Aij star does not contain Aij itself, recall that we eliminated a row and a column. We find that cofactor Aij star equal partial A determinant partial Aij. Why is it so? When the inverse of the matrix exists, we have a little bit complicated. Let me see. Okay. This one, Ij. See, I'd ask if I'm teaching in class, I would ask students whether they understand this. So from here to here, yeah, this expression assume summation convention. Yeah. See, sorry. This assumes summation convention. Summation convention. But here, this I, J are repeated, but this is not summation convention. That means here I or J represent specific number 1 or 2 or 3. Yeah, I think you have to work out to understand more precisely, or to convince yourself. You have to work out somehow. When the inverse of matrix exists, we have inverse of A is it's interesting, no? Where is the inverse? See, I think the complication is this: whether A inverse IJ is it same as this A IJ inverse. And I don't think this is same. I don't think this is true. When the inverse of a matrix exists, I think this is more like this. I would say this is better. If the determinant is not equal 0, you can divide some value by determinant of A, determinant A. So you have this equation. Yeah, I think so. So this one does not mean this is not equal to A inverse IJ. This doesn't mean A inverse IJ. A relation between the permutation symbol and Kronecker delta, known as the epsilon delta identity, is useful in algebraic simplification. Oh, it's complicated. Epsilon ijk, epsilon mnn, mnk equal delta im, delta jn minus delta in, delta jm, ij is no k. From this, when n equals j, so here it's a repeated part is this. K is repeated. So what is assumed is a summation over k, but there is no summation ijmk. And here I, j, n, j, k, n, n, k. No. ijmn. ijmn. No summation. ijmn. No summation about ijnn. Only the summation implied is k. So when n equals j, we get, actually it's easier to see this side. N equals j. This is 1. ijk, mjk, im. Complicated. How come this one n equals j, n equals j. Okay, so there was a theorem, no? I, j, delta. I'm sorry, I got confused about here. So let's consider this part next time. I will consider this next time. Here to here. I got confused. So only 23 page. So I go to 23 page. So we continue